Hello dear students and welcome back to the chemistry class. So for today we have a lot of concepts that we need to discuss, a lot to know, a lot to understand. So let's start this entire session from the first point, and that is going to be the enthalpy change. The enthalpy change that occurs during phase transformation. Now this is quite important. Alright. Now first thing that we need to understand over here is what is the phase transformation. That means a change of a state. For example, if I have taken a solid ice, okay, if I keep it for a longer time at the room temperature, naturally it is going to convert from its solid state into the liquid state. Correct. So here is a phase transformation. That is nothing more than the change in the state. Okay. So whenever there is a change in state, it changes the enthalpy. Okay, it changes the heat contained of a system. We already know that the enthalpy is nothing more than a heat contained of a system. Mathematically, we had also seen that change in enthalpy is equal to the change in the internal energy plus pressure into the change in volume work. Correct. Now, here we have several different phases that we need to discuss. So, the first phase that we need to see over here is the enthalpy of fusion. Okay, so here the term fusion refers to conversion of a solid substance into the liquid one. Okay, so whatever the energy change that occurs when 1 mole of the substance in its pure state is converted into the liquid state at a particular boiling point or a boiling temperature, that particular energy change, we call it as the enthalpy of fusion. Okay, so let's say that this particular enthalpy of fusion is given or it is denoted by the term delta H, change in enthalpy, right? Now, if I am going to add over here as FUS, it becomes as the enthalpy of fusion. Okay, so how did we mention it? What was the definition? The enthalpy change. The enthalpy change that occurs. Okay, that means if you have a particular solid, what change in the energy that occurs? Okay, when 1 mole, now they are very specific over here, 1 mole, okay, so 1 mole of solid substance in its pure state completely melts down. Okay, so what is happening over here? What is the process that is happening? Okay, completely melts down into the liquid state. At this particular transformation from a solid to liquid state, the energy that has been acquired by this particular system, we call it as enthalpy of fusion. Okay, so in order to understand this, let us say that I have water, but let's say I have water in the solid state and that is nothing more than the ice, correct? So if I take ice and if I keep it, what is going to happen? Naturally, after some time at the room temperature, it is going to get converted into the liquid form, correct? So it is quite as melting this particular ice. Okay, so when this melting of ice occurs, so that time the enthalpy of fusion is going to be equal to 6 kilojoules per mole. I hope you people can see that there is a dot over here. So it is a 6 kilojoules per mole amount of energy. Okay, now if you see there is a positive value, that means this particular ice is absorbing 6 kilojoules of energy in order to convert from its solid to its liquid state. Okay, so this particular phenomena we can consider it as the enthalpy of fusion. Now, in case if I am going to reverse this process, so reversing the process in a sense that I have this water, okay, in its liquid form, and if I take this and if I cool down the temperature, and that is nothing more than what we are doing here is we are freezing it. Okay, so when we freeze it, that is nothing more than the same reaction, but it is in reverse form. That time we consider this as delta H of freezing. Okay, so here 6 kilojoules of energy per mole is going to be released. Okay, so what we see is here is the solid ice what we have, it is going to release, okay, this much amount of energy if it gets converted from water to ice per mole. Okay, so I hope you understood this. So in the first case, that is the enthalpy of fusion, in order to convert from the solid to the liquid state, it is absorbing energy. So when it is absorbing the energy, this particular process is becoming over here the endothermic process. Alright, so this particular process is endothermic, while the reverse of this particular process is exothermic. Okay, if you see, the magnitudes are the same, but whether it is absorbing or whether it is liberating the energy, that differs. Okay, so this was our first one, and that is the enthalpy of fusion. Let's see with the next one. So far what we have seen is, we have seen what happens if we are going to convert a solid into liquid. Okay, whatever the energy requirements are there, we call it as the enthalpy of fusion. Correct. Now let's see with the next step, what happens if we convert from the liquid into its vapor state. Okay, so here we use the term as the enthalpy of vaporization. Okay, so enthalpy of vaporization is nothing more than the amount of the heat or the enthalpy change that occurs when one mole of liquid changes or converts into its vapor form. But at what condition it changes from the liquid to vapor? It is at the boiling temperature. Correct? At 1 bar pressure, to be very specific. So the energy change or the enthalpy change that occurs when 1 mole of liquid gets converted into its vapor state at a boiling temperature and 1 bar pressure. We call it as a standard enthalpy of vaporization. Okay, so let me write down that particular statement over here. So enthalpy of vaporization, again, the way that we are going to denote it is delta H of VAP. Now, the enthalpy change that occurs when 1 mole of liquid, of course, in its pure state, we have already discussed about the pure states, correct? In its pure state, is converted. It is converted into the vapors. Correct? But at what kind of conditions? Okay, and it is at its boiling temperature and 1 bar pressure. Okay, whenever you are studying these kind of statements, you need to visualize it. You need to imagine it in order to have an effective understanding of this. You cannot just mug up the things. Okay, so here the enthalpy change that occurs when 1 mole of your liquid which is present in its pure state, is converting into its gaseous state or vapor state at boiling temperature and 1 bar pressure. Now that particular energy change is known as standard enthalpy of vaporization. Okay. Or you can also call it as 1 mole is being used, correct? So we can also call it as molar. So because it is specific to 1 mole over here, so we call it as a molar. Okay, molar enthalpy of vaporization. Okay, we can also go with this particular term, no issues. Alright, so after this, let's see one example which will help us out in order to understand this entire scenario in a perfect manner. So for this, let us say that we have a particular example of water over here. Of course, we are taking water in the liquid state. Now, if I am going to take this and if I am going to heat it, generally what is going to happen? It is going to get converted into its gaseous state. Now, this amount of energy what has been supplied to water, 1 mole of water, again much more specific. So that time whatever the enthalpy change that occurs, we call it as the enthalpy of vaporization, and in this case you are supplying in the energy, and so therefore plus 40.79 kilojoules per mole to be approximate. Okay. So this is how we will understand about the enthalpy of vaporization. Now, there are certain techniques wherein what we do is we directly convert the solid into its vapor state, correct? So, these particular processes wherein we convert a solid directly into its gaseous state without undergoing its liquid form at a temperature just below its melting point. Okay. That particular process, we call it as a process of sublimation. So, what is sublimation? Here, sublimation is nothing more than a process in which the solid is converted, into the vapor state. Okay, into the vapor state without undergoing the change into the liquid state. Correct. But at what point it is happening? At what point this entire scenario is occurring? At the point just below its melting point. Okay. Now, just below the melting point when this entire scenario is occurring, when the solid is getting converted into the vapor state. Okay, that particular process we call it as process of sublimation. Agreed. Now, at this particular process, of course, you need to supply the energy in order to convert from the solids to vapors. Correct. So, the amount of the energy change, the heat energy change that occurs when 1 mole of solid is converted into the vapor state without undergoing any change into the liquid state at a particular point just below its melting point. And that particular energy change, we call it as standard enthalpy of sublimation, or you can just call it as the enthalpy of sublimation. Okay, so the enthalpy change that occurs when 1 mole of solid, what is happening? It it sublimes. I hope you understood. Sublime means this entire process sublimes into its vapor state at a point just below its melting point. Okay, at this particular point, whatever the enthalpy change is there, we call it as is known as the enthalpy of sublimation. Okay, now here we need to undergo one example here. The best example in order to show a sublimation is the iodine pellets. Okay, so the iodine pellets, when it is enclosed in a container, it is usually in the solid state. Okay, so now as we open it and keep it into the open air at the room temperature, it starts getting sublimated into its gaseous form. Okay, so for this particular energy change that is required is delta H of sublimation is equal to, it's going to be around 62 kilojoules per mole. Okay, and 4 kilojoules. Alright, sorry for that. Okay, so this is how, these are the two next processes. So first one we had seen that what happens when we convert solid into the liquid, the enthalpy of fusion. What happens when we convert from liquid to the vapors, and that is going to be the enthalpy of vaporization. Final one, what happens if we directly convert a solid into its gaseous state without interfering into the liquid state. That was sublimation, so therefore the energy change, we call it as the enthalpy of sublimation. Correct. So these are the concepts. Let us see a few more concepts. The next concept that we need to deal is called as the factors affecting the enthalpy change or the enthalpy of phase transformation. Okay, so whenever we take any substance, let it be either in its solid or liquid or in its gaseous states, what usually happens is this entire magnitude of the enthalpy depends upon its intermolecular forces there. Okay, so first thing that you need to understand is if you are taking any substance, let it be any state that you are taking. So in this particular substance, its enthalpy change once you change its phase. The enthalpy change directly depends upon the intermolecular forces. Remember this. So it all depends upon the intermolecular forces. So in short, I would like to say that greater the intermolecular forces acting in the substance, greater is going to be the enthalpy change. Quite simple as that. Okay, so these intermolecular forces, if these are stronger, we'll understand that the enthalpy of this particular system or this particular substance is greater. In order to make this particular concept easier, let us take two examples. Let us say that we have one side water and on the other side, let's say that we have an acetone cation. Alright. Let us say that these are the molecules of water. For a moment, let me say that these are the molecules of water. Okay, and over here, let's say that these are the molecules of acetone. Now, between these molecules, what happens is, between the molecules of water, there are going to be the intermolecular forces of attraction, of course. Correct. Now, these intermolecular forces of attraction in water are hydrogen bondings. Now, hydrogen bonding is very strong strong bond when we compare to that of the bonding which is present between the acetone molecules. So in the acetone molecule, what is happening here? These intermolecular forces, okay, these particular intermolecular forces are actually weaker. Okay, so you can understand here itself that when the hydrogen bond is present, it will see that the water, okay, it will see that this particular water remains in its liquid state. So these hydrogen bondings are much more stronger, and it will see that all of these water is going to remain in its liquid state. So but here what is going to happen is, as the intermolecular forces are weaker, small amount of energy is required in order to overcome these particular forces. Okay, and at the smaller amount of energy itself, we can convert this acetone which is there in liquid state directly into its gaseous states by the help of small amount of water. This is how it goes. Okay, so stronger, if these particular attractive forces were stronger, then this entire system would remain in its liquid state. But what is the problem here is that these particular intermolecular forces of attractions are weaker, as a result of which small amount of energy will change its liquid state into the gaseous state. This is how it would go. Okay, so putting every single thing into a particular conclusion, in a nutshell, I would say that the magnitude of enthalpy. Now, magnitude of enthalpy is greatest, or it is the highest, if you are taking ionic compounds or a solution which is going to contain ionic compound. This is highest. Okay, followed by the next one is going to be polar compounds. The compounds wherein you will see that the particular, what you can say, the intermolecular forces are like an hydrogen bond is occurring. Okay, so, and the least would go for the non-polar. Okay, so non-polar compounds are going to show you the least of the enthalpy change, because they have all weak intermolecular forces in them. Okay, so this is how the entire process goes. So let us start with the next one. The next concept that we need to discuss now is the standard enthalpy of formation. Now, in order to understand this entire process, first I would like to give you an example. First we will see the example, and then we will convert the entire system of this example into the statement. Okay, so let us understand this standard enthalpy of formation. Okay, so quite it is understandable by this particular term as formation. In a sense, we are trying to form something over here, right? So in order to take this into consideration, let us say that we have hydrogen which is in the gaseous form. It is going to react with oxygen, of course, in the gaseous form, in order to give us water. And this water, we will take it in a liquid form, right? Now, in order to balance this, let us say that we have an half, because I am going to just form one mole here. Now, in this entire scenario, the enthalpy change that has occurred is going to be minus 285.8 kilojoules per mole. Alright, so minus sign again, that means amount of the energy is going to be liberated. Okay, so in this entire scenario, what is happening? When the enthalpy change that occurs when 1 mole, I will repeat it again, how much we are forming over here is 1 mole. Okay, so the enthalpy change that occurs when 1 mole of a particular compound is formed from its constituent elements. These are the constituent elements. Okay, from where it is occurring? From its constituent elements. From its constituent elements, of course, in its reference state. Now, the new thing that we have come across over here is the reference state. Okay, now, first we will discuss as what is this reference state. So, reference state is nothing more than, it's same as it is a pure state itself. Okay, it is a pure state of a particular element or a particular substance at 25 degrees Celsius and 1 bar pressure. Now, I can also call it as, this particular reference state as, it is the most stable state of a system at 25 degrees Celsius and 1 bar pressure. You can go with even this statement, okay, or I can write it down as over here as most stable state. Of the system or of a substance at 25 degrees Celsius and 1 bar pressure. Okay, now this particular condition of those particular elements, we will call it as the reference state. So, 1 mole of a compound is being formed from its constituent elements which are taken in its reference state, and that time whatever the enthalpy change that occurs, we will call it as a standard enthalpy of formation. Okay, so let's put every single thing together now. The enthalpy change. The enthalpy change that occurs when it is occurring, when 1 mole, please be proper about this. Okay, so we have been very specific over here. The enthalpy change that occurs when 1 mole of substance is formed from the constituent elements. Okay, from the constituent elements, but these constituent elements are taken in their most stable state, or what we can call it as a reference state. So, from the constituent elements at their reference state. Okay, at that time, whatever this enthalpy change that occurs, we will call it as a standard enthalpy of formation, and this is given as standard enthalpy of formation, that is delta F of H. Okay, so whenever we are saying that standard, please make sure to give this particular knot over here, and as it is a formation, we will give it as F. So this refers to standard enthalpy of formation. So there is one more concept left for this particular video. We'll complete that. Let us begin with the last concept for this particular video, and that is the standard enthalpy of formation as a special case of the enthalpy of a reaction. Now here, in order to understand this entire scenario, first we shall understand a smaller concept of it. Let us say that I have a particular reaction, something like hydrogen, which is in a gaseous form, reacts with bromine, again which is in gaseous form, in order to give us HBr, which is in the liquid state. Okay. Which is in the gaseous state. So, at this entire scenario, in this entire reaction, what we can see is, if we do balance this equation, this is going to become acid to HBr. And at that particular time, whatever the enthalpy change of a reaction is happening here, okay, that is somewhat equal to minus 72 kilojoules per mole. Okay, approximately it is 70.8 kilojoules per mole. Alright. So, when you take a look into this particular reaction gives me enthalpy change for a reaction. Here in this case, it is the enthalpy change for a reaction. Now, when we take a look into the enthalpy of formation, so enthalpy of formation speaks with respect to the formation of a compound. Okay, and this particular compound is formed just for 1 mole. So whenever there is a reaction, and this reaction shows me the enthalpy change in the formation of a compound, and the compound is 1 mole, that time this particular sequence of reaction will become, that energy change will become equal to the standard enthalpy of reaction. In this case, it is just enthalpy of reaction here. Try to understand the difference. So here, this condition is just enthalpy of reaction. It's not a standard enthalpy of reaction in this particular case. Okay, now if I am going to take into consideration of the same equation, let us write it down as H2, that is in the gaseous form, plus Br2, that is again in the gaseous form, and it is going to give rise to, okay, HBr. Let's say it give rise to HBr over here. Now, again in the gaseous form. If I want 1 mole of this particular compound, can I say that I am going to react just 1 hydrogen out of these 2 hydrogen atoms? I am going to react only 1 bromine out of these 2 bromine. So therefore, I am going to get over here HBr. So that time, what is going to happen? Delta HF of this particular thing is equal to delta HR at this particular point. Okay. So this is equal to, so 72.8 divided by 2, we are going to get around 36.4 kilojoules per mole. Now this condition as what you see, wherein the enthalpy of formation, that is nothing more than the formation of 1 mole of this particular compound, correct, is equal to standard enthalpy of a reaction. Standard enthalpy of a reaction means a particular reaction wherein everything is in the standard state and it will give rise to 1 mole of the particular substance. Okay, so in this case, only for this particular reaction, it is equal to, okay, standard enthalpy of reaction is equal to standard enthalpy of formation, and both of them are equal to 36.4 kilojoules per mole. Now, if I see the relationship between these two, that is delta HR, I am speaking only as the enthalpy of a reaction in this case, is equal to delta HF naught. Okay, so here if I see the enthalpy of a reaction is equal to 2 times that of the enthalpy of, standard enthalpy of formation. Alright, so this is how the relationship between enthalpy of reaction and standard enthalpy of formation, and this is how the relation is between the standard enthalpy of formation and the standard enthalpy of a reaction goes by. So make sure that you have observed every single thing very carefully. Okay, these small basics are going to be very helpful, especially when you are going to take a look into the lattice enthalpy, okay, and Hess laws. So in those particular conditions, you will see that these kind of basics are going to be very, very helpful. Okay, so do take care. Thank you for watching. We'll meet you in the next video.